तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Okay, so let us start today with a slight digression, a mathematical digression, and then I get back to Lagrangian dynamics. I would like to move over to Hamiltonian dynamics, and this requires a mathematical transformation with which you are already familiar in other contexts, but perhaps the name was not used, and so let me do that and point out what the advantages are. And this is the so called Ajanta transformation. And the idea in essence is the following: if I give you a simple function of x, a single variable x, then there are two ways of looking at this function. One of them is to say that for every value of x I assign a value of f of x, and therefore if I assign this set of numbers corresponding to each value of x, if I specify the numerical values of f of x for each x, I have specified the function. There is another way of doing it, and that is to say I assign at each point the value of the slope of the function, and at the next point I assign the slope once again and the slope once again, and so on, and in this manner I can build up the function if I specify at each point f prime of x at each point, provided of course I also specify f of x at some reference point. Otherwise of course you could shift this entire graph parallel to itself and it would be exactly the same as before if I just gave you the slope, but if I also tell you f of 0 for instance, then you know where the intercept is, and after that you can reconstruct the function. This is the idea behind the Legendre transform, except that it is not very useful in one variable, but when you have more than one variable it becomes exceedingly useful. So let me give you an example. Suppose you have a function f of x comma y, and then of course you know that you can write its differential df as delta f over delta x dx plus delta f over delta y dy, and this quantity delta f over delta x is some function of x and y. So let me call this capital X of little x, let me use a curly x, so let us use little x in this fashion so you can distinguish between these two quantities, and capital Y of x y dy. By definition capital X and capital Y are these partial derivatives, and now I might want to say that instead of looking at little x and little y as the independent variables, I look at capital X and little y as the independent variables, in other words the slope with respect to x. If I want to do that and I want to construct a function g such that dg is equal to something times d capital X plus something else times d little y, in recognition of the fact that this quantity, this function g is a function of capital X and little y, the trick is very simple. All I have to do is to subtract from f minus little x times capital X, and then of course if I take df, if I define g as equal to this, dg is df minus x capital dx minus capital X times little dx, and of course that term cancels out and you are left with dg to be a function of dx and dy, a combination of dx and dy. Okay. So this is the idea behind the Legendre transform. Invariably you have to subtract out, so let us write down what dg is. Dg equal to df minus x dx minus x dx, and that is equal to minus x dx plus y dy, because this term cancels out on both sides. But you must remember that this little x must be now re-expressed in terms of capital X and little y. So you need to take this equation x of x comma y equal to delta f over delta x, and you have to solve this equation for little x and express little x as a function of capital X and little y. Now once you do that, then you are guaranteed that g equal to g of capital X and little y. Okay. You could go on and say, can I define a function h which is a function of little x and capital Y, and then of course you can do that by defining h is equal to f minus y times y is equal to h of little x and capital Y. You make one more Legendre transform, and finally you could transform to capital X and capital Y altogether. So you could define a function say p equal to p of capital X capital Y. This would be f minus x x minus y y. You can generalize this to any number of independent variables x, y, z, etc. So the whole idea is simply to see what is the most convenient function for your purpose. Very often these f's and g's and so on would be some kind of potentials or some kind of function like the Lagrangian, which I would like to transform to a different set of independent variables for some reason or the other. You are already familiar with this in another context. What is that? Pardon me? The Gibbs potential. In thermodynamics you are used to this thing, because if you recall, we are going to do thermodynamics, but let me recall to you what happens. You start with the internal energy U, and this internal energy you transform, and what is this a function of? What is du a function of? Well, du is Tds minus Pdv for a fixed number of particles. So therefore u is a function of s and v. So this in general du, the first law of thermodynamics, can be written Tds minus Pdv. Actually if you change the number of particles, you also have a chemical potential times the differential in the number of particles. So this of course implies that u is a function of s, v and n as the independent variables, and it is obvious from this that t is delta u over delta s, keeping v and n constant. They are the partial derivatives. Then you might want to consider a function df which is equal to d of u minus ts, and that will now become a function of t, v and n, because df, the tds part is going to cancel from here. There is going to be a tds and an s dt, so it becomes df is equal to minus s dt minus p dv plus mu dn. This implies of course that f is a function of t, v and n. So what you have done is a Legendre transform going from the internal energy u to the Helmholtz energy f, because you would like to have as control variables the temperature, volume and number rather than the entropy, volume and number, depending on your conditions. You might further want to change from pdv to vdp, because you might be able to control temperature, pressure and number. Then what do? You go from this f by subtracting f minus pv plus pv, because there is already a minus sign here, and what would this give you? dg here, and that is equal to minus s dt plus v dp plus mu dn, and that implies that g is a function of t, p and n. because dg is proportional to a combination of dt, dp and dn. So depending on what your external conditions are, what your experimental conditions are, if you can handle temperature, pressure and the number as your control variables, then you would like to have the Gibbs free energy as your thermodynamic potential. These are all thermodynamic potentials, and you go from one to the other depending on your convenience, depending on the kind of processes you want to look at. And then of course you know in thermal equilibrium, in a state of thermal equilibrium, if you are at constant entropy, volume and number, then the internal energy is at a minimum. If you are in a stage where the temperature, volume and number are constant, then in thermal equilibrium the Helmholtz free energy is at a minimum, and similarly for the Gibbs free energy. So this is the reason for going from one thermodynamic potential to another, simply so that you can handle, you can first write a minimum principle, and secondly you can decide on what your experimental control variables are. Much the same thing is going to happen in the Hamiltonian framework, going from the Lagrangian to the Hamiltonian. It is going to be a Legendre transform. So how do I do that? Again, let me simplify notation a little bit. Our Lagrangian, which is a function of q1 to qn, q1 dot to qn dot and possibly t, I have written an abbreviated notation as L of q, q dot and t. It is actually a function of 2n plus 1 variables in general, the generalized coordinates, the generalized momenta and possibly time if it is a non-autonomous system. I would like to get rid of these velocities and use the partial derivatives of L with respect to these velocities as the independent variable. So I would like to use delta L over delta qi dot as the independent variable, and let me call this and define this to be equal to p sub I, and I call it a generalized momentum. You can see why I am doing this, because we already saw from the Euler-Lagrange equations that if you have delta L over delta qi equal to d over dt qi dot, then we know that if qi is a cyclic coordinate or ignorable coordinate, this quantity here is a constant of the motion. So every time you have a cyclic coordinate, the corresponding momentum, generalized momentum, is a constant of the motion, and this is how invariances would start coming in. Constants of the motion would be identifiable. So let me define right now once and for all delta L over delta qi dot as the momentum, the generalized momentum conjugate to the corresponding generalized coordinate, and I will explain the meaning of this word conjugate, but they go in pairs. What happens if I do this? I would then like to go from an L to a new function h, which is a function of the q's and the p's collectively, p1 to pn I write as p, and possibly t. And how should I define it? I should define this as L minus the product of the q dots with the corresponding p's, but historically one did it with a reverse sign, it does not matter. So let me define this as summation over I equal to 1 to n qi pi qi dot pi minus L. All I have done is to change a sign, and the reason is H is going to turn out to be the total energy of systems, mechanical systems in particular, and therefore I would like to retain a plus sign for it, no other reason. Could have done it as L minus q dot qi dot pi, but let us leave it at this. However, H is a function of q, p and t. Velocities do not appear in the Hamiltonian. This quantity is called the Hamiltonian and velocities do not appear in it. So how are you going to get rid of these velocities? They are sitting here, right here. So what you are supposed to do is to solve this set of equations and write qi dot as a function of all the q's, p's and possibly time. So you have to take this quantity, differentiate it, and then of course you get a function of q, q dot and p, and you are supposed to eliminate if possible the different qi dots and write them, express them explicitly as functions of q's, p's and t's. And after that you plug that in here, and wherever q dots appear here you again write them as functions of q's, p's and t's, and if you can do this then this is a function of q, p and t in principle. Now when would you be able to do this? When can you actually do this? It is not obvious that you can always eliminate. If you have one variable it is not so easy, it is not so difficult if you have a single q, p and t, but if you have a multiple set of quantities then it is not so obvious that you can do this. And I put it to you that, and I will explain this later on by example, we will see this, that if this matrix of quantities qi dot delta qj dot, this is some function, this is labeled by the indices I and j, and it is obviously can be written as a 2 by 2 matrix. If that matrix is non-singular then you can always make this change of variables, you can invert this set of quantities. This is called the Hessian matrix corresponding to this transformation. We will come back, we will look at examples. Just want to point out here that you should be able to make this transformation, otherwise there is no point in it. Now let us assume that we can do so, and let us ask what happens next. Alright, I pretend I have done this. Now what happens next? What should I do? I should try to find out if h is indeed a function of q's, p's and t's and what it implies. So let us do that and see what happens. So dh therefore becomes equal to, again let me save myself a little bit of trouble by assuming that I write this as q dot p, forget the I here and you can put the summation and put the indices in explicitly and so on. Okay. So dh becomes dq dot times p plus q dot times dp minus dl. Now what is dl? Well, this is equal to pq dq dot plus q dot dp minus delta L over delta q dq minus delta L over delta q dot dq dot minus delta L over delta t dt. I just take the differential on the right hand side, L being a function of q, q dot and t, you can write dl in that form. On the other hand, dh itself should be writable as delta h over delta q dq plus delta h over delta p dp plus delta h over delta t times dt. Now let us compare both sides. We already know that delta L over delta q dot is in fact p, sorry, by definition. Therefore this term cancels out against this term, and now we are in good shape because p, q and t are independent variables, and if this is equal to that, the coefficients of dq, dp and dt must be equal to each other, since these are completely independent variables. Now what does that imply? This immediately gives us a set of consequences. If I compare, for example, this with that, it says q dot equal to delta h over delta p. So that has matched this with that. Now I match this with that, and here is where the physical input is going to be. What do I get? I get delta L over delta q equal to delta h minus delta h over delta q. But remember, we are talking about solutions of the Euler-Lagrange equations. We are going to use the equations of motion. On these solution trajectories, delta L over delta q by the Euler-Lagrange equation is known to be delta L over delta q equal to d over dt P, it is delta L over delta Q dot, which is P, and therefore this equation here becomes P dot equal to minus delta H over delta Q. And I erase that, and of course if I compare this with that, for non-autonomous systems it turns out that delta L over delta T is minus delta H over delta T. This therefore is now the content of the Euler-Lagrange equations that has been put in, and since this is the set that you arrive at, incidentally notice that this definition P equal to delta L over delta Q dot has a conjugate, has a corresponding counterpart, which is this: Q dot is delta H over delta P, whereas P is delta L over delta Q dot. So it is again the slope, and that is just telling you that you can always go from the Hamiltonian to the Lagrangian back with the Legendre transform, and this is precisely the Legendre transform. So that is not very surprising, but this equation here contains dynamics because the Euler-Lagrange equations have been put in here. This set of equations is now exactly what you want. What is the advantage of this set of equations over the Euler-Lagrange equations? They are first order equations, they are explicitly first order equations in the 2n dynamical variables. So the great advantage is that we have reduced this second order set of equations to a first order set of differential equations by going to the Hamiltonian framework. But you are going to do a lot more, you are going to gain many more advantages, and what are they, and let us start writing them down. So far I have not defined the Hamiltonian as anything more than PQ dot minus L. I have not said it is the total energy of the system, I have not identified it with the total energy. This depends on what L would be, but as far as I am concerned, you give me a system with a Lagrangian, and provided I can make the Legendre transform, I can always go to the Hamiltonian, whatever function that be, and then once you have that function you end up with this set of first order differential equations, and I now forget about the Euler-Lagrange equations and focus on solving this set of equations, but it has got magical properties. So again let us write this down: Q dot is delta H over delta P, P dot equal to minus delta H over delta Q. The minus sign is crucial, the most important minus sign in the universe, okay, it is absolutely crucial. You will see what it does as we go along. The first point is that if H is independent of time explicitly, then H is a constant of the motion automatically. How do we find out? Well, if H is equal to H of QP, say, so this is autonomous, it is an autonomous system, then what is dH over dt equal to delta H over delta Q Q dot plus delta H over delta P P dot by definition. But on a solution trajectory, namely when Hamilton's equations apply, so I should call this Hamilton's equations. This is going to be our starting point in some sense. When these equations apply, then I replace Q dot by delta H by delta P here. So this becomes delta H over delta Q, delta H over delta P minus delta H over delta P over delta Q, and you see the role played by this minus sign, so this becomes identically 0. The Hamiltonian is therefore a constant of the motion as long as it is not explicitly dependent on time. So this is the way you discover a constant of the motion. This is always true for every Hamiltonian system which is an autonomous system, explicitly time independent Hamiltonian. You are guaranteed that the Hamiltonian is a constant of the motion. It is going to play a very, very fundamental role, and what is that? You already begin to see that it has a favored role over all other constants of the motion, which we are now going to try to deduce. The reason being that the way in which the phase space point changes its velocity is governed by the Hamiltonian. So in that sense the Hamiltonian governs the time evolution of a system, and therefore we call it the infinitesimal generator of time translations, because it is telling you if you give me q's and p's at any instant of time t0, at t0 plus delta t the Hamiltonian tells you where the system goes, where the point goes, and so on. So this is going to have a very fundamental role to play in all that we are going to do. We will write down the Hamiltonian for simple systems, but in general please notice that the Hamiltonian as written here, this function, is a very very special role to play. You could ask, what about other constants of the motion? What does a general constant of the motion look like? Well, let us do that, and can we relate it to the Hamiltonian? So constant of the motion, suppose f is a constant of the motion. In general of course it is a function of all the q's, p's, and it could be explicitly time dependent. Please notice a constant of the motion could be explicitly time dependent, because the time dependence which comes from the explicit time dependence could be cancelled by the time dependence of the p's and q's. So in general of course a given system, dynamical system, will have constants of the motion which are time dependent. Some of them would be time dependent. I will give you a simple example in a minute, but what does this imply? It says df over dt equal to delta f over delta q, q dot, but q dot should be replaced by delta h over delta p, because you are on a solution trajectory, plus delta f over delta p times p dot, but p dot is minus delta h over delta q, so there is a minus here, delta q, plus of course delta f over delta t. Now this little structure here has very profound implications, a very deep meaning which I will come to very shortly. This set of partial derivatives, please notice I abbreviated my notation. If you have n degrees of freedom, it really stands for I equal to 1 to n with an I here, it really stands for that. And this object which is constructed out of two functions f and h is called the Poisson bracket of f with h, and by definition is denoted as f curly bracket h plus delta f over delta t. It is the Poisson bracket of f with h. It plays the same role in classical mechanics as the commutators of matrices or operators would in quantum mechanics, and in fact the translation from classical to quantum mechanics through the Poisson bracket is very immediate, and we will see that. So you agree this is some function of q's, p's and t's. After you finish this set of complicated set of partial derivatives, it is some function of p's, q's and t. And when is f a constant of the motion? If df over dt vanishes identically. This means f is a constant of the motion if and only if the Poisson bracket of fh plus delta f over delta t equal to 0. If f should turn out to be explicitly time independent, then the last term goes away, and then f is a constant of the motion if and only if its Poisson bracket with the Hamiltonian vanishes identically, and I would then say it Poisson commutes with h, in analogy with what happens for in quantum mechanics, where I would say two operators commute with each other. In that sense I would say this Poisson bracket is 0, I would say they Poisson commute. The other word that is often used is f and h are said to be in involution with each other. I will write that down a little later when we write down the criterion for integrability, but at the moment I want you to focus on the point that the way you test if some quantity is a constant of the motion now is simply to calculate this set of partial derivatives and check if it is 0 or not. If it is 0, identically it is a constant of the motion, if it is not, then it is not a constant of the motion. Now of course this structure here has some deep implications. You could define the Poisson bracket of any two functions of phase space variables. So you could have some A which is a function of all the q's and p's and t perhaps, and some B, and this Poisson bracket here is defined as delta A over delta q dot delta B over p dot minus the reversed partial derivatives, and it has some properties, and the first property is that this is equal to minus BA. And that is immediately obvious, you reverse A, interchange A and B and you get a minus sign out there. By the way, there is an even more trivial property which essentially says that A plus B with C is A with C plus B with C. That is of course true. Immediately all you have to do is to plug it in there, and this is at once true. And similarly, if you took A and multiplied it by some constant with B, this becomes alpha times AB. So multiplication by a constant does not do anything, it just comes out of the partial derivatives. So this property here, this antisymmetry, is a crucial property of the Poisson bracket. There is another property which is also a crucial property, and I will explain why that is so, but for that we need a preliminary. You should ask what is A with B C, where A, B and C are functions of the phase space variables q's, p's and possibly t. What is this equal to? Well, put that in here, you have an A here and a B C here, and then you expand this out. If you do that, you discover this is equal to B times A with C plus A with B times C. So it has this chain rule kind of property, and of course if these are functions, this is a function and that is a function of phase space variables, everything commutes. So I could have written this B on the right hand side, that C on the left hand side, it would not make a difference, but I have in mind always going over to quantum mechanics where these would be operators, matrices or operators, then of course AB is not equal to BA, and this is the correct order. Since B appears on the left here and C on the right, that is exactly how it appears everywhere. B always appears on the left and C on the right, it does not get commuted, and that is why I put this B on the left here and C on the right there. Now I leave you to figure out what AB with CD is. You have to apply this formula repeatedly and so on. So this is the way you would find Poisson brackets of various complicated functions of the phase space variables given a few elementary Poisson brackets. And the first of these, before I do that, let me mention the property I was interested in here. This property is easy to verify. First take the Poisson bracket of B with C, it is some function, take the Poisson bracket with another function A and do this in cyclic order. So B with C A plus C with AB, and the answer turns out to be 0 identically. To do this you have to verify this property using that expression, using this relation here, using this formula you can verify that this is actually valid, and this is called the Jacobi identity. We will see what its use is in half a second, but you see this tells you that if you take 3 of these functions and you do this in the cyclic order repeatedly and you add it all up, you get 0. Now this property together with this property, for a set of elements, any abstract set of elements A, B, C, D etc., elements of a class, if it should so turn out that you can define a bilinear operation between them, in other words something which involves 2 of them at a time and produces another member of this class, and here they are phase space functions. So you take two phase space functions, find the Poisson bracket, you produce another phase space function of the phase space variables. If you can define a bilinear operation among them which is antisymmetric, which has a minus sign when you interchange two members, and for which the Jacobi identity is valid, such a set of elements is said to form a Lie algebra. This plus this together imply that the set of elements is a Lie algebra. You are familiar with other examples. One of them is immediately matrices. If you took n by n matrices and defined the bilinear operation to be the commutator AB minus BA, then of course that is equal to minus of BA minus AB, and the triple commutator is 0 identically. So matrices, n by n matrices under the operation of commutation form a Lie algebra. Functions of phase space variables for a system form a Lie algebra under the Poisson bracket operation. Can you give me another example? One which you are very familiar with in 3 dimensions. You are very, very familiar with it. Yeah? A cross B, ordinary vectors would do exactly this, because you know that if you took two vectors and you take the cross product, you find another vector. So this is certainly true. A cross B equal to minus of B cross A, and you know the triple product A cross B cross C plus B cross C cross A plus C cross A cross B is also 0. So ordinary 3-dimensional vectors under the cross product operation form a Lie algebra. There are numerous other examples, but these are the simplest ones, and they are going to have, this is going to have very profound properties, as we will see very, very shortly. Okay. So any questions at this stage? So we have seen what a constant of the motion is. It is something which in the autonomous case is independent, its Poisson commutes with the Hamiltonian, and we have also seen that the Hamiltonian itself is a constant of the motion. Now the next question one should ask is, given these properties, can we write these down in a more compact form? What is the real meaning of the Poisson bracket? What is the geometrical meaning of the Poisson bracket? This is worth asking. I mean, why does this particular combination of things really turn out to be so fundamental? That is the first question. The other question is there something I can do to put this whole business in the language of general dynamical systems? What makes Hamiltonian systems so special, so very special? And the answer is the following. Recall that our general dynamical system involved variables x1, x2 up to xn, and we had an equation x1 dot is f1 of all the variables xn, and so on up to xn dot n. In our case, instead of a vector field f1 to fn here, a single scalar function, namely the Hamiltonian, is determining the right hand sides completely. So that is a great simplification, because instead of having a vector field on the right hand side, you have q1 dot is delta h over delta p1 q right up to qn dot equal to delta h over delta pn, and then you have a p1 dot is minus delta h over delta q1 up to pn dot is minus delta h over delta qn. Our phase space variables x in this case are really q1 to qn, p1 to pn. So we have a situation where 2n equal to n. The phase space is even dimensional for a Hamiltonian system, and I write all the q's one after the other and then all the p's one after the other, and I call that a vector in phase space, a position vector in phase space. Then this quantity here tells you that the velocity of the phase space point is determined by certain partial derivatives with respect to a scalar function h, It almost looks like a gradient. It almost looks like a gradient, because what would the gradient operator be in phase space? This would be delta over delta q1, delta over delta qn, delta over delta p1, delta over delta pn. This is my gradient operator, and it would be very nice if I could write x dot equal to the gradient of h. Is this true? It is not true, because this is not q1 but p1 unfortunately, and this here is not p1 but q1 and a minus sign to boot. So it is not quite the gradient. However, you can make it look like the gradient as follows. Let us define a matrix J to be equal to 0, the unit matrix minus the unit matrix, and 0, where this thing is an n by n unit matrix. And this here stands for the n by n null matrix. Let me define a matrix, big matrix capital J, to be a 2n by 2n matrix in 4 blocks. The top block, top left hand corner block, is just the null matrix, so is the bottom right hand corner block, and then the identity matrix in the off diagonal positions, and the minus the identity in the lower right hand side. Once I do this, then it is a trivial matter to check that this set of equations, this entire set of equations, could be written as x dot equal to j times the gradient of h. So this says q1 dot on top would be the first component, delta h over delta q1 right up to delta h over delta pn, but then you apply the J matrix on the left hand side, and you will pick out just the right quantity, because out here would be a 1, the top end here, that 1 would pick out for q1 dot precisely this quantity here, delta h over delta p1. So this makes it look almost, not quite, but almost like a gradient system. But the fact is, all the simplicity that you gain by saying that your vector field on the right is derived from a scalar field are going to be present right here, except it is a sort of twisted gradient. It is not quite the gradient, but a twisted gradient. Incidentally, this minus sign came from the Euler-Lagrange equations, so we can't wish it away. It is sitting there, and it was a good thing it was there, because it gave us the information that the Hamiltonian is a constant of the motion itself, as long as you have autonomous systems. So this gradient here is called the symplectic gradient. Okay. I will explain why this word symplectic is used right here, but right now it is terminology. It is called the symplectic gradient of H. This matrix J has interesting properties which we will need. J squared equal to minus the identity matrix, and that is easy to verify, and this, by the way, stands for 2n by 2n identity matrix. And that immediately tells us that J inverse equal to minus J, because J inverse is minus I, so J inverse is minus J. So J has an inverse and it is equal to minus itself, and incidentally it is a trivial matter to see that this is also equal to J transpose. If I interchange the rows and columns of this matrix, if I write the ij element as the Ji element, then that is just going to give me minus J. Okay. Very useful properties. Can we say something about the Poisson bracket now? And the answer is yes, because you can now see that what we wrote as a comma b as summation I equal to 1 to n delta a over delta qi delta b over delta pi minus delta a over delta pi delta b over delta qi. This is what the Poisson bracket was by definition, can also be written as, well, delta A over delta Qi and then delta A over delta Pi suggests that you are taking the gradient in phase space of this quantity A, the scalar function A. So what is happening is that this quantity is equal to gradient A transpose. By gradient A I mean a vector with elements delta A over delta Q1, delta A over delta Q2, etc., written as a column vector. By transpose I mean the corresponding row vector, and that is getting multiplied by gradient of B, which is a column vector, but because you have this minus sign, not surprisingly you have a j in between. Now what would you say if I wrote a column vector and wrote a row vector on the left hand side? So in ordinary space, if I have a column vector a1, a2 up to an, and then I have b1, b2, bn, and this stands for the vector a and this stands for the vector b, then of course once I write it in this notation, all I have done is to take b dot a, the dot product, because it is b1 a1 plus b2 a2, etc., and that is just the dot product, the ordinary dot product. That has been replaced by a symplectic dot product. So this is a symplectic scalar product, and it is telling you that a and b, these two functions in phase space, their symplectic dot product of their gradients is the Poisson bracket. Now go back to ordinary Euclidean space. What happens if I tell you that you have two functions f of x, f and g, functions of the space coordinates, such that the gradient of f dot product with the gradient of g is 0? What would you say about the functions f and g? So I tell you gradient of f dotted with gradient of g equal to 0, or in matrix notation grad f transpose grad g is equal to 0. What geometrical information do you get by saying the gradient of this function and the gradient of that function dot product is 0? Yeah, their level surfaces are perpendicular to each other or orthogonal to each other. So this is telling you that if the Poisson bracket of A with B is 0, then it says the level surface of A and the level surface of B are orthogonal to each other in the symplectic sense with this metric put in here. So this is why I said that people often say that Hamiltonian dynamics is the study of symplectic geometry. So you have to pretend that your phase space, the q's and p's, have this extra j sitting in there when you want to define dot products, when you want to define the gradient and so on. Now once you do that, then you have what is called symplectic geometry or a symplectic metric, and the whole of Hamiltonian dynamics has this very elegant geometrical interpretation. Yeah.
So what do you mean by perpendicular in the symplectic sense?
With this metric. Now I am going to come back to this and explain when we do relativity what I mean by orthogonality when you have non-Euclidean metrics. Okay. So this is something which we will explain a little later, but right now you can see that once I put in this j appropriately at various spots, these things start looking like Euclidean geometry, except I have to put in this j once in a while to take care of all these minus signs. So this is in fact the significance of the Poisson bracket. This is the way to look at it. This is by the way an algorithm to calculate the Poisson bracket, but its real meaning is here in this place here. Okay. Now let us come back, step back a little bit and do one more thing which is absolutely crucial for a normal Hamiltonian system, and that is to define what I meant by this word conjugate momentum. I did not define that yet, so let us do that.
The order of gradient of the gradient.
Pardon me?
Order of gradient.
What is meant by the order means?
Order means is it a vector of n by 1 or
This guy here, by this I mean a column vector which is delta b over delta q1 up to delta b over delta pn. Oh yes, everything here includes p. You can't talk about the q's and p's separately. The whole phase space is 2n dimensional always, but I by convention said I am going to write the first n components as the q's and the remaining n components as the p's. I could have inverted it, as you will see later on, but it does not matter, I am going to stick to this convention. This is my definition of a phase space point, this is my definition of gradient, the del operator in phase space always. Very shortly we are going to see that it does not matter which variables you call the q's and which variables you call the p's, you can actually exchange. These are generalized coordinates and generalized momenta, and there is a deep symmetry between them in any case. I am not saying the physical dimensions of a length and a linear momentum are the same, not saying this, but apart from dimensionality you can always interchange variables. So the beauty of it is, although we started out from very humble beginnings, this is telling us there is something extremely deep going on in nature, and the fact that dynamics is happening in phase space is not an accident, it has got a very deep geometric structure. Now let me define what is meant by conjugate. Recall that our independent variables were qn, p1 up to pn, and I could ask what is the Poisson bracket of say qk with ql, what is this equal to? And certainly qk and ql are dynamical variables, phase space variables, and I could ask what is the Poisson bracket of this with that. So this is I equal to 1 to n delta qk over delta qi delta ql over delta qi minus in the reverse, sorry, pi minus the reverse term. But you see the q's and p's are independent variables, completely independent variables, so this is 0, therefore it is 0, this is completely 0, so this is equal to 0, identically 0. In exactly the same way pk with pl is identically 0, and the reason is at some stage when you do this partial derivative you are going to take this function and differentiate with respect to q, and that is identically 0. But it is another matter if you ask what is qk with pl, and this is not going to be 0, what is this going to be? Summation I equal to 1 to n delta qk over delta qi delta pk over delta pi pl minus delta qk over delta pi delta pl over delta qi, and this term is 0 because the p's do not get differentiated with respect to the q's, nor do the q's with respect to the p's, so that is gone. When is this term equal to a non-zero quantity? When k equal to I, otherwise it is 0 because these are independent variables, therefore this is equal to summation over I delta ik, a Kronecker delta ik, and this of course is Kronecker delta IL, and you have to sum over all possible i's, and this is going to be 0 unless k is equal to I, this is going to be 0 unless L equal to I, the free indices here are k and L, and therefore this is equal to delta KL, just the Kronecker delta of k with L. So that defines for me the canonical Poisson bracket relations. This set of relations are called the standard or canonical PB. Poisson bracket relations. And once these relations are satisfied, then I say that the momentum Pk is conjugate to the momentum in the generalized coordinate Qk, or Qk and Pk form a conjugate pair. So all the phase space variables get broken up into pairs, and notice here that each Qk Poisson commutes with all the other p's except its conjugate when the Poisson bracket is equal to 1 on the right hand side. This is very familiar in some sense, because if you look at positions and momenta in quantum mechanics, the commutator of the position coordinate, one component with another is 0, momentum similarly is 0, but position with momentum, the right hand side would give you an IH cross times the unit operator if these are conjugate variables. This is the germ of that, it is starting to do that already. So that relation in quantum mechanics was actually arrived at from here in some sense, follows from this place. So there is in fact a correspondence which will tell you how to go from Poisson brackets to commutators in quantum mechanics, and the Hamiltonian framework lays the groundwork for that. Now of course once you are given these relations and the Poisson bracket formulas, you can find the Poisson brackets of any functions whatsoever, and let us write down what the Hamiltonian is for a simple system like the simple harmonic oscillator and see how this works. So I have, for instance, you could do this in general, you could do this for a set of particles. So if I have a system for which the Lagrangian as a function of q dot is equal to, I look at an autonomous system now, is equal to 1/2 the kinetic energy plus minus the potential energy, and the kinetic energy is equal to well, you could take a general function, but let me take 1/2 mi qi squared summed over I over all the particles 1 to n minus v of q1 to qn, and this is an example. So I have in mind a Lagrangian which is just whose independent generalized coordinates are just the Cartesian coordinates of a set of particles, call them q1 up to qn, and the potential which is a function only of the coordinates, no explicit time dependence here. What is the Lagrangian in this case? First of all, what is pi? This is delta L over delta pk, delta qk dot, and this is equal to mk qk dot, because only that qk is going to get differentiated and it gives me this mk qk dot. And indeed in this simple example it is clear that the momentum is the mass times the velocity and vice versa, the velocity is 1 over mass times the momentum. Does not always have to be true, the real definition is sitting here in this place, and therefore what is the Hamiltonian in this problem? The Hamiltonian is equal to summation over I pi qi dot minus L, but that is equal to summation over I pi, but for qi dot I have to put in this here and invert this expression here and write the q dot in terms of the p, because remember the Hamiltonian is a function of the q's, p's and time possibly. So this becomes pi dot and another pi dot, so divided by mi minus, that takes care of this part, minus 1/2 summation over I mi, this is q dot squared, qi dot squared, but I have to write qi dot as pi dot divided by mi, and when I do that pi squared over mi squared plus the potential V of q, and that gives you the familiar expression 1/2 I pi squared over 2m plus V equal to t plus V. This is how you identify for such systems the Hamiltonian with the total energy of the system. So the minus sign which we used in defining L has disappeared and it has become a plus sign here, and this is the reason I chose to define the Hamiltonian as pq dot minus L rather than L minus pq dot, so that I would get the total energy. And now since we know the Hamiltonian is a constant of the motion for autonomous systems, we know immediately that this combination here provides you with the first constant of the motion, and in many cases we simply write down the Hamiltonian as t plus V, but you must express it in terms of the momentum. Now let us look at the other example very quickly. of the particle in a charged particle in an electromagnetic field. What happened there and what happened to the momentum? Remember the Lagrangian as a function of r, v and possibly t was equal to 1/2 m v squared plus q a dot v minus q phi. So what is the momentum p conjugate to the position r? This is delta L over delta v. I am sorry to abuse notation. By this I mean, I do not mean to differentiate with respect to a vector, by this I mean a vector formed by differentiating L with respect to each component separately. So just shorthand for it, it is like the gradient operator in velocity space. I just write it casually in this form, and this is equal to mv, but here you have to differentiate this with respect to v, and it turns out to be qa. So that gives us a very important relationship which says that the momentum conjugate to the position for a charged particle in an electromagnetic field is not the mechanical momentum, which would be mass times the velocity, but it also involves the field explicitly. There are many names given for this, but I would like to simply call it the conjugate momentum. Or the canonically conjugate momentum, and this is sometimes called the mechanical momentum. Also sometimes called the kinematic momentum, which is what it is for normal motion without the presence of a field. But it is important to remember that P is not equal to mv. That it is not in most cases, it is not if the particle is moving sufficiently fast, it is certainly not equal to mv itself, but here you also have the field appearing, the potential appearing here. Now you should ask a very deep question immediately once I tell you P equal to mv plus qa. What would that be? Pardon me? Say this slowly. A is not unique. A is not unique, it is not gauge invariant. And it looks like we have ended up with trouble because you have a momentum which I said is a phase space variable and physical, and now I am telling you it involves A. It seems to be gauge dependent. This is going to lead us to some trouble, but let us see what happens. Let's go ahead with this. What is the corresponding Hamiltonian? And then I stop here, we take it up from that point. H of r and p and maybe t in this problem is equal to, you plug this back in here, you can solve for this of course, put it back in here, and then it will turn out that this will turn out to be p minus qa whole squared over 2m plus q phi. That is the Hamiltonian of a charged particle in an electromagnetic field. P is just replaced by p minus qa. The p of the free particle is replaced by p minus qa, and you are guaranteed, absolutely guaranteed, that the Poisson bracket of px with x or x with px is 1, x with y with py is 1, and so on, provided you use the symbol p for this combination here in this case. I leave it to you as an exercise to now write down the Hamilton equations of motion and verify that it is exactly the same as the Euler-Lagrange equation, the Lorentz force equation that we got. But notice the plus sign here, this plus has appeared here, and A has appeared here in a strange way. Although it appeared linearly there is a quadratic term here, there is a term which depends on A squared. So it is almost as if A is inducing itself. This is related to the phenomenon of diamagnetism. The fact that you have this A squared term is going to be non-trivial. There are many other non-trivial things that are going to happen. If I square this, there is a p dot A term, there is an A dot p term, and that does not matter in classical mechanics, but in quantum mechanics A is going to depend on r, and therefore p dot A is different from A dot p, and you have to keep track of that. But this is going to give us the right answers. This is the correct Hamiltonian for a charged particle in an electromagnetic field, and we will see what happens if I make a gauge transformation on this, what is going to happen to this H, and it is going to be related back to the fact that you can add a total time derivative to the Lagrangian and nothing happens. But we have to ask what is the meaning of that statement in the Hamiltonian framework, what is the corresponding thing, and it will turn out it corresponds to something called a canonical transformation, which does not change the physics of it. So again all these things are closely linked to each other, and there is a very intricate machinery, but I will start tomorrow next time. I will start with this point and we will look at a few problems in Hamiltonian mechanics, especially with regard to stability and so on. So after. Good question. Let me give the detailed answer to that next time. It says, is the Hamiltonian more physical than the Lagrangian? No, I do not say that at all. I do not say that. I will list the advantages and disadvantages of each of the two formalisms, and then you will see that they are just as physical.
Is canonically